NENOMATICA, where mathematics meets YouTube excellence. The seventh law of power. Welcome to our math lesson on negative exponents. In this video, we're going to learn what negative exponents mean and how to work with them. Let's start with the fundamental rule for negative exponents. When we have a value a raised to a negative exponent negative m, this equals 1 divided by a raised to the positive exponent m. Let's understand this with a simple example using the number 3. We'll create a table showing different powers of 3 and observe the pattern. Do you notice the pattern? As we decrease the exponent by 1, we divide the result by 3. Going from 3 cubed to 3 squared, we divide by 3. 27 divided by 3 equals 9. Going from 3 squared to 3 to the first power, we divide by 3 again. 9 divided by 3 equals 3. And from 3 to the first power to 3 to the 0th power, dividing by 3 again. 3 divided by 3 equals 1. If we continue this pattern, what would 3 to the negative 1 power be? We would divide 1 by 3 again, giving us 1/3 or 1 over 3. This confirms our rule. 3 to the negative 1 equals 1 divided by 3 to the 1. Now let's generalize this pattern for any non-zero number, a. We can create a similar table for a raised to different powers. What about a to the negative 2 power? Following our pattern, a to the negative 2 would be 1 divided by a squared, or 1 divided by a times a. This confirms our general rule. A to the negative m equals 1 divided by a to the m. Let's begin with our example. In this problem, we need to understand what negative exponents represent. The theorem states that when a base is raised to a negative exponent, it equals 1 divided by the same base raised to the positive version of that exponent. In other words, a to the power of negative m equals 1 divided by a to the power of m. This is one of the fundamental properties of exponents. It allows us to convert between negative exponents in the numerator and positive exponents in the denominator. Let's see how to prove this important theorem. Let's assume that m is a positive integer and a is a non-zero number. We'll start our proof by using the division property of exponents. We start with the zero power rule, which states that any non-zero number raised to the power of 0 equals 1. So a to the power of 0 equals 1. Now, we'll divide a to the power of 0 by a to the power of m. By the division property of exponents, when we divide powers with the same base, we subtract the exponents. So a to the power of 0 divided by a to the power of m equals a to the power of 0 minus m, which gives us a to the power of negative m. On the other hand, since a to the power of 0 equals 1, the left side of our equation can be written as 1 divided by a to the power of m. Since both expressions are equal to a to the power of 0 divided by a to the power of m, we can equate them. Therefore, a to the power of negative m equals 1 divided by a to the power of m. Let's start with our first example. We need to convert 0.00001 to a negative exponent form. First, let's write this number as a fraction with 1 in the numerator. 0.00001 equals 1 over 100,000. Next, we recognize that 100,000 is equal to 10 to the power of 5. So we can write our fraction as 1 over 10 to the 5th power. Finally, we can use the negative exponent rule, which states that 1 over x to the n equals x to the negative n. Applying this rule, we get 10 to the negative 5 power. Let's move on to our second example. We need to convert 1 over bc to a negative exponent form. First, let's rewrite this fraction using exponents. Since b and c each appear once in the denominator, we can write them as b to the first power and c to the first power, giving us 1 over the product b to the first power times c to the first power. Now, applying the negative exponent rule, we can rewrite this as bc to the negative first power. For our final example, we'll convert 0.008 to a negative exponent form. First, let's rewrite this decimal as a fraction. 0.008 equals 8 divided by 1,000. Next, we can rewrite this using powers. 1,000 is 10 to the power of 3, so we have 8 divided by 10 to the 3rd power. We can also rewrite the numerator. 8 is equal to 2 cubed, so our fraction becomes 2 cubed divided by 10 cubed. Now, let's examine this fraction more carefully. We have the ratio of two different bases raised to the same power. We can rewrite this by using the property that 2 divided by 10 equals 1/5. So we have 1/5 cubed. Finally, we can apply the negative exponent rule. 1/5 cubed is equivalent to 5 to the negative third power. So our final answer is 5 to the negative third power. We have the expression 1 over 3 to the power of 11. First, we can rewrite this as 1 over 3 to the power 11. Using the negative exponent rule, we can rewrite this as 3 to the power negative 11. So the final answer is 3 to the power negative 11. Let's move to our second example. Here, we have 1 over 4 to the power 5. First, similar to the previous example, we can rewrite this as 1 over 4 to the power 5. Applying our negative exponent rule, this equals 4 to the power negative 5. We can take this further by recognizing that 4 is 2 squared. So 4 to the power negative 5 is equal to 2 squared to the power negative 5. Using the power of a power rule, this becomes 2 to the power of 2 times negative 5, which is 2 to the negative 10. So our final answer is 2 to the power negative 10. Let's look at our final example. We have the decimal 0.25. First, we need to recognize that 0.25 can be written as a fraction, which is 25 over 100. This fraction can be simplified to 1/4. 1/4 is the same as 1 over 4 to the power of 1. Using our negative exponent rule in reverse, we can write this as 4 to the power negative 1. Since 4 equals 2 squared, we can rewrite this as 2 squared to the power negative 1. Using the power of a power rule, this becomes 2 to the power of 2 times negative 1, which is 2 to the power negative 2. So our final answer is 2 to the power negative 2. Let me show you an alternative method. We could also approach this by writing 0.25 as 0.5 times 0.5, which is 0.5 squared. Since 0.5 equals 5/10, we can write this as 5/10 squared. 5/10 is the same as 1/2, so we have 1/2 squared. 1/2 is 2 to the power negative 1, so we have 2 to the power negative 1 squared. Using the power of a power rule, this becomes 2 to the power of negative 1 times 2, which is 2 to the power negative 2. This confirms our earlier result. 0.25 equals 2 to the power negative 2. To summarize what we've learned today, first, the key rule for negative exponents is that a to the power negative n equals 1 over a to the power n. Second, when we have an expression in the form 1 over a to the power n, we can rewrite it as a to the power negative n. And finally, we can use additional rules like the power of a power rule to further simplify expressions with negative exponents. These techniques allow us to convert between different representations of the same value, which is a powerful tool in algebra. Let's begin with the basic rule for negative exponents. When we have a base raised to a negative power, we can rewrite it as 1 divided by the base raised to the positive power. For example, x to the power of negative n equals 1 over x to the power of n. Now, let's work through some examples from the image. Our first example is 3 raised to the power of negative 5. To solve this, we'll apply our negative exponent rule. 3 to the power of negative 5 equals 1 over 3 to the power of 5. So our answer is 1 over 3 to the 5th, or 1 over 243. Let's move to our second example. We have 1/5 raised to the power of negative 4. When we have a fraction raised to a negative power, we can first apply the negative exponent rule. This gives us 1 over 1/5 to the power of 4. Then we can simplify further using another rule. When a fraction is inverted, the numerator and denominator switch places. So 1 over 1/5 equals 5 over 1, which is just 5. So we have 5 to the power of 4, which equals 625. Let's look at our third example, which involves multiplying expressions with negative exponents. We have 2/3 raised to the power of negative 3 times 2/3 raised to the power of negative 4. When multiplying expressions with the same base, we add the exponents. So we get 2/3 raised to the power of negative 3 plus negative 4, which is negative 7. Now we apply our negative exponent rule. 2/3 to the power of negative 7 equals 1 over 2/3 to the power of 7. We can simplify this as 1 over 2 to the 7th over 3 to the 7th. This equals 3 to the 7th over 2 to the 7th. So our final answer is 3/2 to the power of 7. Our final example is slightly different. We have a to the power of -2 times b to the power of -2. When multiplying different bases with the same exponent, we can use the product rule, which tells us that a to the power of m times b to the power of m equals a times b all to the power of m. So a to the power of -2 times b to the power of -2 equals a times b all to the power of -2. Now we can apply our negative exponent rule. This gives us 1 over a times b all to the power of 2. This simplifies to 1 over a squared times b squared, or 1 over a squared b squared. To summarize what we've learned about negative exponents: 1. For any non-zero number, a to the power of -n equals 1 over a to the power of n. 2. When we have a fraction to a negative power, we can either apply the negative exponent rule first, or we can invert the fraction. Let's solve the given problem. We have a to the -3 times b to the third times c cubed to the -2 power. Let's begin by addressing the negative exponents in our expression. The first property of exponents we'll use is that a to the negative power is equal to 1 over a to the positive power. So a to the -3 can be rewritten as 1 over a cubed. Next, we'll apply the power to a power rule for the term c cubed to the -2. The power to a power rule states that when we raise a power to another power, we multiply the exponents. So c cubed to the -2 becomes c to the power of 3 times -2, which is c to the -6. Now, we'll apply the negative exponent rule once more for the term c to the -6. Using the same rule we applied earlier, c to the -6 can be rewritten as 1 over c to the 6th. Now, we can reorganize our expression. We have 1 over a cube times b cubed times 1 over c to the 6th. We can combine these terms, placing the denominator terms in a single fraction. This gives us b cubed over a cube times c to the 6th. We need to rewrite the following expression in exponential notation: the quantity 4x to the -4th power, y to the 5th power, all raised to the power of 3. To solve this problem, we'll use the power of a product rule, which states that when a product is raised to a power, each factor in the product is raised to that power. Let's apply this rule to our expression. We'll raise each term inside the parentheses to the power of 3. So we get 4 to the 3rd power times x to the -4 times 3 power times y to the 5th times 3 power. Next, we'll use another rule: the power of a power. When a quantity with an exponent is raised to another power, we multiply the exponents. Applying this rule to the variables with exponents, x to the -4 cubed equals x to the -12, and y to the 5th cubed equals y to the 15th. For the coefficient, we calculate 4 cubed, which is 64. Let's review the rule for negative exponents. A negative exponent means we take the reciprocal of the base raised to the absolute value of that exponent. Now, let's rewrite our expression using the negative exponent rule. We get 64 times the fraction 1 over x to the 12th power times y to the 15th power. We can simplify this further to 64y to the 15th power over x to the 12th power. Let's move on to our second example. We need to rewrite the following expression in exponential notation: the quantity -10z squared y to the -4th power, all squared, times the quantity z cubed y, all raised to the 5th power. Let's tackle this step by step. First, we'll apply the power of a product rule to each group. For the first group, -10 squared is 100, z squared is z to the 4th power, and y to the -4th squared is y to the -8th power. For the second group, z cubed to the 5th power is z to the 15th power, and y to the 5th power is y to the 5th power. Now, we'll use the rule for combining like terms with exponents. When multiplying powers with the same base, we add the exponents. Let's combine the like terms. For the z terms, we add the exponents: z to the 4 plus 15, which gives us z to the 19th power. For the y terms, we add the exponents: y to the -8 plus 5, which gives us y to the -3rd power. Now, let's apply the negative exponent rule again to rewrite y to the -3rd power as 1 over y cubed. Finally, we get 100z to the 19th power over y cubed, or equivalently, 100 over z to the -19th power times y cubed. Let's summarize the rules we've used. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.